In this section, we'll go ahead and construct the graphs of sine and cosine. Before we do that, let's go ahead and review the coordinates of our right triangles that lie on the unit circle, specifically our special right triangles. We'll only be reviewing this for the first and second quadrant, but the pattern is going to remain the same. Let's go ahead and work with quadrant 1 first. Here we have our xy plane, but we're only looking at the first quadrant. And here we have our unit circle. Let's draw the special right triangle determined by the angles 30, 45, and 60. This first triangle is determined by 30 degrees. This next triangle will be determined by 45 degrees. And our last triangle will be determined by 60 degrees. The coordinates of the blue point are given by the square root of 3 divided by 2 and 1/2. The coordinates of our terminal green point are given by the square root of 2 divided by 2 and the square root of 2 divided by 2. And the coordinates of our terminal red point are given by 1/2 square root of 3 divided by 2. Now let's look at these special right triangles that lie in quadrant 2. Again, we have our xy plane, but we're only going to care about the second quadrant. Let's define these in terms of reference angles. So this terminal point will be determined by the reference angle of 30 degrees. Our green point will be determined by the reference angle of 45 degrees. And our red point will be determined by the reference angle of 60 degrees. Then the blue terminal point has the coordinate values negative square root of 3 divided by 2, 1/2. Our green reference, our terminal point, is determined by the values square root of 2 divided by 2 and square root of 2 divided by 2. And the red terminal point will have coordinate values negative 1/2 square root of 3 divided by 2. So now that we have these terminal points on our unit circle, we can go ahead and use these special right triangles to go ahead and evaluate sine and cosine. Let's make a chart of our input values given by theta and our output values given by sine theta. We're going to be evaluating a lot of these here, but please look back and refer to the terminal points in quadrant 1 and quadrant 2 for the first half. We want to evaluate our function at 0, pi divided by 6, pi divided by 4, pi divided by 3, pi divided by 2, 2 pi divided by 3, 3 pi divided by 4, 5 pi divided by 6, pi, 7 pi divided by 6, 5/4 pi, 4 divided by 3 pi. Let's keep going. 3 divided by 2 pi, 5 divided by 3 pi, 7 divided by 4 pi, and 11 divided by 6 pi. Evaluating our function sine at these values, we're going to get the following values. 0, 1/2 square root of 2 divided by 2, square root of 3 divided by 2, 1 square root of 3 divided by 2, square root of 2 divided by 2, 1/2, 0, negative 1/2, negative square root of 2 divided by 2, negative square root of 3 divided by 2, negative 1, negative square root of 3 divided by 2, negative square root of 2 divided by 2, negative 1/2, and finally when we get back to 2 pi, this will be given by 0. Let's go ahead and draw our sine function using these points here. Before we draw these, let's go back and look at these pictures here. Recall that The triangle determined by angle 30 has a blue terminal point, the triangle defined by angle 45 has a green terminal point, and the triangle determined by a red terminal point is given by 60. So we'll be using these colors to correspond to the points on our sine graph. The points I just drew will be the blue points, which correspond to either angle 30 or reference angle 30. The green points will correspond to angles of 45 or reference angle 45. And the red points will correspond to angles of 60 degrees or reference angles of 60 degrees. Then our black points correspond to values of theta that are given by 0, pi divided by 2, pi, 3 pi divided by 2, or 2 pi. And here is our sine graph. So I'm going to ruin our sine graph now by drawing a line through it. And what we'll see is since trig functions are defined by angles and right triangles, they will repeat values in sets of 2 pi. We'll talk about this more after we draw the graph of cosine. Let's go ahead and do the same thing, but this time I won't write everything out. I'll give you our functions, I'll give you the values theta and the evaluations cosine of theta, and then we'll draw the graph from 0 to 2 pi. Again, we're looking at theta, and we want to evaluate this at cosine theta. Like I just said, let me go ahead and write this out first. Now that we have the values, let's go ahead and graph these, again, using points that correspond to points on the unit circle. Again, our blue points are going to correspond to points that are determined by the angle of 30 degrees or reference angle 30 degrees. Then the green points correspond to points on the unit circle that are determined by 45 degrees. And finally, the red points are points on the unit circle that are determined by angle 60 degrees or reference angle 60 degrees. Last but not least, the black points in our graph correspond to points on the unit circle that lie either on the x-axis or the y-axis. Now, connecting the dots on our graph, we'll see that the shape of our sine function looks like the following. Again, sine and cosine are very beautiful functions, but it's hidden beneath the definition. Now that we see the basic structure of the graph from 0 to 2 pi for both sine and cosine, we can go ahead and extend this from negative infinity to infinity. Again, the way we can do this is because trig functions have repeated values in sets of 2 pi. This comes from the fact that a terminal point on the unit circle is determined by theta, and theta plus any multiple of 2 pi. What this means is that sine evaluated at theta plus 2 pi, let's say times k, will always be equal to sine evaluated at theta, and for the exact same reason, if we evaluate cosine at any multiple of theta plus 2 pi k, this will always be equal to cosine theta. These types of functions in general are called periodic. Let's write the definition down of a periodic function. In this definition, the number t is called the period. From this definition, what we do know is that sine and cosine have a period of 2 pi. Given this information, we can now extend the graph of sine and cosine from negative infinity to positive infinity. Here we have our sine theta, where this part of the graph is going from 0 to 2 pi, and this part of the graph is going from 2 pi to 4 pi. On the negative side of the graph, we have that this is going from negative 2 pi to 0. Maybe drawing this one more time to get rid of any of the bumps in the graph. In general, our sine function will look like the following. Now, by extending our cosine function, we'll get a picture that looks like the following, where again, the period's given by this part of the graph here. This is our first period from 0 to 2 pi. We have another period from 2 pi to 4 pi. And in this last piece over here, if we had a little more room, this would be from negative 2 pi to 0.